Okay, think about this. You tap buy online, you book a flight, maybe just stream a movie, all that stuff that just works.
Seamless, right.
Yeah, seamless. But underneath, it's built on these incredibly complex layers. Databases, APIs, integrations. It's like this hidden digital plumbing.
Uh-huh.
Hmm.
And you interact with it constantly every single day, probably without giving it a second thought.
Exactly. Until something goes wrong, then you definitely notice.
Right, when the pipes burst, so to speak.
So today, we're going to pull back the curtain. We got a whole stack of sources from a listener who wants to get into the real technical weeds. How are these systems built? How do they stay running?
Yeah, we're diving into database administration design, changes, keeping things available, and also tackling the, let's say, fun world of system integration and API troubleshooting based on some articles.
Our mission for this deep dive, to give you a glimpse into the, well, often kind of ironic reality behind our smooth digital lives. We'll cover the key ideas, some surprising details.
And maybe give you a new appreciation for the sheer complexity involved. It's the nuts and bolts making the internet hum, or sometimes groan.
Okay, let's dive in. Let's start at the foundation. The data itself and the folks who guard it.
The database administrators, or DBAs, they're the custodians, really,
Yeah.
making sure your data is safe, accessible, performs well.
And it sounds like a pretty good gig, according to the sources. In demand, good growth prospects, well paid.
It is a critical role, yeah, high demand. But here's where that irony kicks in. The job description, it basically seems to include knowing, well, everything.
Everything.
Everything touching the database, the OS, the storage, networking, sometimes even application logic. They're expected to be experts on the whole ecosystem.
Wow. Okay. That's broad. And I saw something about the hours, too. Not
Ah.
exactly 9 to 5.
Definitely not. The average DBA, according to one source, works over 50 hours a week, often weekends, too. Because database problems, they don't really keep business hours.
Wait, they happen at 2 a.m. on a Sunday.
Exactly. So you're often on call, expected to fix things under pressure.
And what else makes it tough? There was something about blame.
Ah, yes. The database is often guilty until proven innocent. That's how the source puts it. If an application slows down, guess who gets the first call?
The DBA, even if it's not their fault.
Precisely. You might get developers rushing in saying, hey, DB2 is broken, fix it so my brilliant code can run. When the issue might actually be, well, the brilliant code.
Huh. Okay, I can picture that. High pressure, always on call, got to know everything. So how do these essential folks actually start building these data stores? Let's talk data modeling.
Right, the blueprint phase.
Mm-hmm.
Super critical. You start by figuring out what data you need, how it all connects. There's the conceptual model, high-level business view.
Like customers, orders, products.
Then you drill down into the logical model. That's the nitty-gritty. Data types, text, numbers, dates how long they are, the relationships. Like one customer has many orders. That kind of detail. Cardinality normalization.
Normalization. That's about making the data tidy, right? Less repetition.
Exactly. Reducing redundancy, improving integrity. Like first normal form, 1NF, is basic stuff. It just means each piece of data is atomic. You don't stuff multiple phone numbers in one field. You give each its own entry. Simple idea, but fundamental.
One piece of info per box. Makes sense. So you've got the logical plan. Then what?
Then you translate it into a physical database. The actual tables, indexes, storage settings. This is physical design. And, while there are roles like database architect, often it's the DBA doing this too.
More hats for the DBA. Okay, what are some key technical things they nailed down here?
Referential integrity is huge. Building those links between tables, primary keys, foreign keys, and rules, like don't let someone delete a customer if they still have open orders. Keeps data consistent.
Prevents orphaned data. Got it.
Then there are indexes. They're absolutely vital for performance. So like shortcuts to find data quickly without reading the whole table.
Like the index in the back of a book.
Perfect analogy. But here's the catch the sources mention. The database decides if it wants to use an index for a query. The DBA designs them based on how they expect the data to be used.
Hoping the database optimizer agrees.
Pretty much. And if it doesn't use the index or the right index isn't there, slow query, table scan. Not good.
Okay. And I saw a note about indexing by workload versus indexing by object. What's that about?
That's really important. A common mistake is just putting basic indexes on primary keys, maybe a few other columns. Indexing by workload means you actually look at the real queries hitting the database and design indexes specifically to speed those up. Much more effective.
Tailoring it to actual usage? Smart.
Yeah.
What about where the data physically sits? Storage stuff.
Also key for performance. Things like putting data files and index files on separate disk drives, if possible, to reduce I/O contention. Less important maybe with super-fast SSDs, but still a consideration.
And compression. Seems like a no-brainer, saves space.
It does save space, yeah.
Yeah.
But it's a trade-off. Compressing and decompressing takes CPU cycles. But
Oh.
because the data is smaller, you might need fewer disk reads to get what you need, which can actually improve I/O speed. So you trade CPU for potentially faster I/O. It's a balance, like most database tuning.
Always trade-offs. And they have to keep an eye on space usage constantly.
Oh, yeah. Monitoring free space, how tables are growing, fragmentation. Running out of space is generally considered bad. Stops everything.
Okay, so they build it carefully. But things change, right? Businesses need new features, data structures evolve. Changing a live database sounds tricky.
Tricky is putting it mildly. The sources are pretty blunt. Today's big database systems don't make structural changes easy or fast.
But don't you just use an alter table command?
You can, for some things. Alter table add e-column exists, but for many changes like changing a data type, adding a column in the middle, repartitioning a simple alter often won't cut it. You frequently have to drop the object and recreate it.
Snap a live table and recreate it. That sounds disruptive.
It is, and incredibly risky. And here's the kicker the sources highlight: the cascading de-drop effect. If you drop something high level, like a table space, a storage container, the database might automatically drop everything inside it to maintain consistency.
Everything meaning.
Meaning the tables, the columns, the keys, all those carefully designed indexes, triggers, views, synonyms, plus all the security grants and the performance statistics. Gone. Poof.
Wow. One command unleashes chaos.
Total chaos if you're not careful. The DBA has to meticulously script out all the definitions of the DDL for everything that's going to be dropped before they drop it. Capture security grants, stats, then drop, recreate the base object, and then painstakingly run all those scripts to rebuild everything else in the right order.
That sounds terrifyingly complex and prone to error.
It really is. And the irony: a seemingly simple request like, can we add this one field, can explode into this massive high-stakes database surgery.
And you have to sync it with application changes too, right?
Absolutely. If the database changes, but the app code isn't updated at the same time, the change is useless or, worse, breaks the app. Constant coordination needed.
Okay, so designing, building, carefully changing. Now, just keeping the lights on. Availability and performance. The source is called availability, the holy grail.
And it is. If the data isn't available, apps don't run, business stops. Simple as that. And with everything online, 24/7 availability is increasingly the standard expectation. Downtime costs real money.
What keeps DBAs up at night? What causes outages?
Oh, the list is long. Hardware failures, servers, disks, OS crashes, database software bugs, bad patches. Human error is a big one, unfortunately. Network problems, data corruption, losing objects, losing the whole database, losing the data center.
Yikes. So how do they fight back? How do they aim for that 24/7 uptime?
Good backups are baseline, obviously. But for high availability, use things like standby databases, basically hot spares ready to take over fast.
Yeah.
And clustering is huge. Things like Oracle RAC, IBM Sysplex, multiple servers working together as one database. If one server fails, the others keep going.
Share the load, provide failover.
Exactly. The sources also touch on NoSQL databases, sometimes being used for specific, super high availability needs where maybe a traditional relational database struggles. Different trade-offs there, though.
Right. So that's keeping it available. What about keeping it fast? Performance tuning.
Yeah, equally important. Performance management is about making sure the database uses resources efficiently. CPU, memory, I/O, getting the most work done, and reducing contention, where different processes are fighting for the same resource and slowing each other down.
When things are slow and fingers point at the database, what are the usual suspects?
Top of the list, bad SQL. Queries coming from applications that are just inefficient, causing full table scans when an index exists, making poor choices about how to join tables, using clunky subqueries.
So the database could be perfectly designed, but bad code tanks performance.
Happens all the time. Other common culprits are outdated statistics, the info the optimizer uses to make decisions, inefficient application logic, like looping over SQL calls unnecessarily and locking problems, where one process holds a lock too long and blocks others.
And tuning isn't just tweaking the database settings, is it?
No, absolutely not. It's the physical design, yes. Indexes, table parameters, but it's also the database instance configuration, memory allocation for caches, things like that. Plus the operating system, the network, and crucially, the application code itself. It's a whole system problem. Proactive planning helps, but yeah.
Okay, let's widen the lens now. Beyond one database, connecting different systems. System integration. Sounds simple. Sources say it's anything but.
Oh, it's a major source of pain. That anatomy of the heart source really spells out the challenges. Data mapping and transformation is a big one.
Like System A calls something customer id and it's a number, System B calls it client ref and it's text.
Exactly. And making sure they actually mean the same thing semantically. Converting between these formats is hard, error-prone. You could lose data, corrupt data, and unstructured data makes it even messier.
And security. Must be a headache across systems.
Huge headache. Poor integration is a security risk. And just getting systems to talk securely is often where things fall down first. Authentication, proving who you are, and authorization, what you're allowed to do. API keys getting mixed up, oath flows failing, very common.
Plus compliance GDPR, HIPAA.
Adds layers and layers of complexity when data flows between systems. You have to track and secure it everywhere.
And scalability. Systems need to handle more load as the business grows.
Right. Integrations that weren't designed for scale just break. They buckle, as the source says, become bottlenecks. Then you're looking at major, expensive re-engineering work.
Seems like a lot of technical traps, but I found it interesting that the sources link many technical problems back to people and process issues.
That's a really key insight. Unclear requirements, teams lacking the right skills, scope creep, simply underestimating how complex integration is. These non-technical factors often cause the technical failures down the road. Treating integration as just IT work, not core business strategy.
Better planning, maybe treating it more strategically, could prevent some pain.
You'd hope so. Clear goals, right resources, understanding the business impact definitely helps.
Okay, so things will break eventually. How do you play detective and troubleshoot these complex integrations?
Yeah, troubleshooting isn't just fixing, it's learning. Documenting what went wrong, how you fixed it, that helps next time. The sources emphasize that systematic approach.
How do you even know an integration failed? Where did the symptoms show up?
Usually the business feels it first. Operations slow down, data's missing or wrong, decisions get delayed, customers get frustrated, maybe financials are impacted. The ripple effect goes far beyond the IT department.
So you know something is broken in this web of systems. How do you isolate the problem?
Divide and conquer is key, using techniques like mocking or stubbing. If your process talks to 3 external APIs, you might create fake versions of 2 of them to see if the problem is really with the third one, or maybe just within your own code.
Reduces the variables, makes it manageable.
Exactly. Otherwise, you're lost in complexity.
Let's drill into API specifically. Authentication authorization failures sounds like a frequent blocker.
Oh, yeah. If System A can't prove its identity to System B or doesn't have permission for the requested action, bang, dead stop. Usually you get a specific error code back.
HTTP status codes, the sources mentioned using those.
Yeah, they're your first clue. 4XX errors generally mean the client your system did something wrong. 400 bad request, 401 unauthorized, 403 forbidden, 404 not found, or 429 too many requests, hitting rate limits.
And 5XX errors.
That usually means the server, the API provider, had a problem. 500 internal server error, 503 service unavailable. First step is always check the API docs, double check your request headers, body, everything. Maybe use a tool like Postman or curl to test the call in isolation.
Rate limiting hitting those API usage caps. How do you deal with that?
Monitor your usage. Set alerts. Cache data you don't need to fetch constantly. Maybe use batch processing if the API supports it. Fewer, bigger calls instead of lots of small ones.
And if calls fail temporarily, that exponential back-off thing.
Crucial for retries. Don't just hammer the API again immediately. Wait a second, then 2, then 4, then 8. Progressively longer waits.
Gives the service time to recover.
Exactly. And add some randomness, jitter, so not all your systems retry at the exact same microsecond. And be smart. Don't retry a 404, the thing just isn't there, but maybe retry a 500 or 503. Check those docs.
Data quality seems like another recurring nightmare in integration.
For sure. Garbage in, garbage out. If the source data is bad, inconsistent, missing values, duplicates, it pollutes everything downstream. You need data profiling to find the problems and data cleansing to fix them, ideally before integration. And validation rules everywhere.
Like the Salesforce validation rules example, checking data as it comes in.
Precisely. In the source, in the integration layer, in the target. Catch bad data early.
Okay, none of this troubleshooting works without visibility. That brings us to logs and monitoring, the digital detective partner.
Couldn't do the job without him. Logs tell the story. Who did what, when, what happened, any errors. Trying to debug without logs is painful. You need access logs, error logs, performance logs, security logs.
And just having logs scattered everywhere isn't enough, right? Centralization.
Absolutely critical. Especially when one request flows through 5 different microservices, you need to see the whole journey in one place. Centralized logging tools help with that, and standardization consistent formats for timestamps, severity makes them usable.
Tools like ELK Stack, Splunk, Signaz were mentioned.
Yeah, tools to collect, search, and visualize logs are essential. And beyond logs, you need metrics, numerical measures of performance.
Response time, error rate, throughput.
Yep. APM application performance monitoring tools collect this telemetry. You track availability, is it up? Performance, is it fast? Error rate, is it failing? Usage, how busy is it?
And you set up alerts and dashboards based on that.
You have to. Get alerted before it becomes a major outage. Dashboards give you that quick visual check on system health.
We also saw webhooks mentioned briefly as a different way to integrate than just constantly asking any updates.
Right, polling versus push. A webhook is when System A tells System B something happened by sending a notification, usually an HTTP request with data, to a specific URL.
Like an event notification.
Exactly. System A sends the payload, often JSON. The key thing from the sources is that System B needs to acknowledge receipt super fast, like send a 200 OK response back immediately, usually within seconds.
Why so fast?
Because if System B tries to do all the heavy processing, update its database, call other systems before sending the OK, it'll probably time out. The sender System A will think it failed and might retry, causing duplicates.
So acknowledge quickly, then process.
Yep. The best practice is
Yeah.
get the webhook, send 200 OK, put the payload on a queue, like SQS or RabbitMQ, and let a separate worker process it asynchronously. Decouples receipt from processing. Apps reliability.
Makes sense. More robust. Security mentioned too, HTTPS and signature.
Yeah. Need to make sure webhooks are secure, verifying the sender, encrypting data.
And finally, tools like Jira for tracking the troubleshooting process, collaborating, and HubSpot mentioned as a place data might end up.
Right. Just highlighting that this involves process, collaboration, and integrates with all sorts of business platforms. It's not just code, it's workflow.
Wow. Okay, we've really journeyed through the hidden machinery today.
From the database administrators keeping the core data safe and sound,
To the often frustrating world of connecting systems and hunting down bugs when they don't talk nicely.
it's definitely a realm of deep technical challenges, constant vigilance, and trying to manage ever-growing complexity.
And that irony keeps popping up, doesn't it?
Yeah.
The smooth experience you get relies on people wrestling with this complexity, expected to know practically everything, working long hours, and often being the first call when anything goes wrong anywhere in the chain.
It really does highlight the intense human effort and maybe the inherent fragility under that polished digital surface.
Which leaves us with a final thought, maybe. In systems, this tangled layer upon layer, dependency upon dependency, is there ever really one single root cause when something breaks?
Or is it almost always a combination of things? A perfect storm of small issues aligning just wrong across different components.
Something to maybe think about next time an app is slow or a site gives you an error.
Definitely food for thought.
All right, that wraps up this deep dive. Thanks for joining us. We'll see you next time.